nice day. In this video, we look into crystal field theory as applied to octahedral complexes. I am Dr. V.Gomathi, Associate Professor, PG and Research Department of Chemistry, Sithalakshmi Ramaswamy College, Tiruchirappalli. The contents of the topic are postulates of crystal field theory, shapes of d orbitals, splitting of d orbitals in octahedral complexes, distribution of electrons in T2g and Eg orbitals in octahedral complexes, calculation of crystal field stabilization energy. Crystal field theory was proposed by the physicist Hans Bethe in 1929 to describe the bonding in coordination complexes. Postulates of crystal field theory. The central metal cation is surrounded by ligand which contain one or more lone pair of electrons. The ionic ligands, for example, fluoride ion, chloride ion and cyanide ion are regarded as point charges, and the neutral molecules, for example, water and ammonia are regarded as point dipoles. If the ligand is neutral, the negative end of this ligand dipole is oriented towards the metal cation. The bonding between the metal and the ligand is purely electrostatic. That is, the bond between the metal and the ligand is 100% ionic. Shapes of d orbital. Before we enter into the splitting of d orbital in octahedral complexes, we must aware that the shapes of the d orbitals. The orbitals which have their lobes along the axis are called axial orbitals. These are dz square and dx square minus y square orbitals called as Eg orbitals. E refers to doubly degenerate. G refers to gerade. This is dx square minus y square orbitals. The lobes of these orbitals lie on x and the y axis. This is dz square orbitals. There are two lobes on the z axis and there is a doublet shaped ring that lies on the x and y plane around the other two lobes. The orbitals whose lobes lie between the axes are called non-axial orbitals. These are dxy, dyz and dxz orbitals are called as T2g orbitals. T refers to triply degenerate. This is dxy orbitals. The lobes lie in between x and the y axis. This is dyz orbitals. These lobes of the orbitals lie in between y and the z axis. This is dxz orbitals. The lobes of the orbitals lie in between x and the z axis. Consider a free metal ion. These free metal ions, the orbitals, the pi d orbitals of the metal ions are degenerate d orbitals. The pi d orbitals of the metal ions are called as degenerate d orbitals. That is, all the pi d orbitals have same energy. Consider an octahedral complex of the type ML6N plus. The central metal cation is surrounded by 6 ligand octahedrali. Both the ligands on each of the three axes approaches the central metal cations. The electrons in the d orbital of the metal cations repelled by
The negative point charges are negative end of the dipoles of the ligands. Because of this repulsion, the energy of the d orbitals are increased. The energy of the pi d orbitals are raised by same amount. That is, all 5 d orbitals are still same in energy. That is, this is also the degenerate d orbitals. But this is a hypothetical situation because the lobes of the EG orbitals, which lie directly in the path of the ligand, experiences greater repulsion. That is, the electron present in the EG orbital experience greater repulsion than that of the T2G orbital. Because of this greater repulsion of the electron present in the EG orbital, the EG orbital's energy is raised compared to the T2G orbital. So the splitting of d orbital into two groups, Eg and T2G, in presence of ligand field is called crystal field splitting or energy level splitting. This is the degenerate d orbital of the free metal ion. This is the d orbitals are still having degenerate, but it is having higher in energy. This is crystal field splitting of d orbital into two sets. One is Eg and another one is T2G. The energy difference between Eg orbital and T2G orbital is referred as delta O. O in delta O indicate octahedral environment. This is represented as delta O or 10 dq. The Eg orbitals are zero point 0.6 delta O or 6 dq higher in energy than the hypothetical situation. The energy of the T2G orbital is zero point 0.4 delta O or 4 dq less than the hypothetical environment, that is barycenter. Distribution of electrons in T2G and EG orbitals in octahedral complexes. Based on alpha principle and Hence rule, T2G orbitals are filled up first and then EG orbitals are filled up. The distribution of electrons takes place based on the nature of the ligands also. If the octahedral complexes containing strong ligands, the strong ligands exert strong field on the central metal cation, hence high splitting power. That is, the delta O value is greater than pairing energy in case of strong field complexes. In case of weak field complexes, there is a lesser interaction. The splitting power is less. That is, delta O value is less than the pairing energy in case of weak field complexes. The octahedral complexes containing 10 electron in the d orbital, that is, it is a d10 system. In case of strong field complexes, the electrons are, that means the 6 electrons are first enter into the T2G orbital and the 4th electrons are enter into the EG orbital. That is, the first 6 electrons getting paired up into the T2G orbitals and the 7, 8, 9 and 10th electrons are enter into the EG orbital in case of strong field complexes. Because in case of strong field complexes, the delta O value is higher compared to the pairing energy. So the electrons are getting paired up in the T2G orbitals are first, and then the electron enter into the EG orbital. In case of weak field complexes, the same D10 system, the first three electrons are enter into the T2G orbital, the fourth and the fifth electron enter into the EG orbital, then 6, 7 and 8 electron enter into the T2G orbital. The last two electrons again enter into the EG orbital. That is, in case of weak field complexes, the delta O value is lesser compared to the pairing energy. So, first three electrons enter into the T2G orbital, and the fourth and the fifth electron enter into the EG orbital. Then only pairing takes place in case of weak field complexes. In case of strong field complexes for D4, D5 and D6 ions, there is less number of unpaired electron. Here in case of strong field complexes, there is a less number of unpaired electron. So, the strong field complexes are otherwise known as paired electron complexes or low spin complexes, because in the strong field complexes, in the strong field ligands, the number of unpaired electron is less. So the resultant spin is less, so it is called as low spin complexes. But in case of weak field complexes, especially in case of D4, D5 and D6 ions, the number of unpaired electron is higher in case of weak field complexes. So the weak field complexes, that is the spin-free complexes, are otherwise known as high spin complexes. Crystal field stabilization energy is defined as the change in energy due to splitting of d orbital of metal cation under the influence of ligand field in a complex. That is, it is the magnitude of energy difference between the two sets, that is T2G and EG orbital. The stability of the complex increases as the amount of crystal field stabilization energy increases. Calculation of crystal field stabilization energy. The energy difference between the T2G and EG sets of orbital is measured in terms of crystal field splitting parameter delta O or 10 dQ. Crystal field stabilization energy is the number of electrons in T2G orbital into minus 0.4 delta O plus the number of electrons in EG orbitals into 0.6 delta O. In case of D6 ion, for a strong field complexes, the 6 electrons are enter into T2G orbitals. That is, the number of electrons in the T2G orbital is 6 into minus 0.4 delta O plus the number of electrons in EG orbital. Here there is no electron in the EG orbital, so here it is 0 into 0.6 delta O. The crystal field stabilization energy for D6 ion in case of strong field complexes is minus 2.4 delta O. The same D6 ion in case of weak field complexes. Here, the 3 electrons are first enter into the T2G orbital, the 4th and the 5th electron enter into the EG orbital, the 6th electrons getting paired up in the T2G orbital. So, here the crystal field stabilization energy is equal to the number of electrons in the T2G orbital, that is 4 into minus 0.4 delta O plus number of electrons in EG orbital. Here the electrons in EG orbitals is 2 into 0.6 delta O. 4 into minus 0.4 delta O, this is equal to minus 1.6 delta O plus 2 into 0.6 delta O, which is equal to 1.2 delta O. So the crystal field stabilization energy in case of D6 ion for weak field complexes is minus 0.4 delta O. Thank you.